nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del sitio.
Huehue, diálogos a través del tiempo.
Alejandro Frank es físico y se integró al Colegio Nacional en el 2016. Frank ha desarrollado trabajos en la mecánica cuántica y es pionero y fundador en la teoría algebraica de la dispersión. Para Alejandro, la dispersión algebraica es una metodología matemática para describir la interacción entre las partículas. En mecánica cuántica hay un principio que no permite saber con qué velocidad se está moviendo un sistema, pero sí saber dónde está, o al revés, saber su velocidad, pero no su ubicación. Pero Frank desarrolló un método para saber ambos, la velocidad y la posición. Lo logró analizando un sistema en su transición de fase. Para este tipo de análisis se necesitan modelos teóricos muy complejos. Frank describe a la mecánica cuántica como una técnica matemática especialmente capaz de describir a la naturaleza, y sus investigaciones sobre la teoría algebraica de la dispersión las aplicó en este campo. Octavio Novaro Peñalosa fue físico y miembro del Colegio Nacional desde 1995. Una de las ramas que más le debe a Novaro es la industria petroquímica por sus estudios sobre fuerzas intermoleculares y catálisis teórica. Los catalizadores son partículas muy pequeñas de metales preciosos y Novaro los describía como piedras más pequeñas que las aspirinas, con el poder de acelerar las interacciones entre las moléculas del hidrocarburo. Y el resultado era genial, reacciones químicas en menor tiempo, lo que implicaba usar menos energía y menos recursos. Sucede que una vez extraída la materia prima de los pozos petroleros y después de que se reservan en plantas colosales, se deben calentar a muy altas temperaturas para lograr su reacción. Y para acelerar este proceso se les agrega una dosis de catalizadores. Después de la expropiación de Lázaro Cárdenas, México estaba obligado a desarrollar métodos propios que no dependieran de una concesión extranjera para obtener productos derivados del petróleo a menor tiempo y menor costo. Samuel Gittler fue ingeniero civil, matemático y miembro del Colegio Nacional desde 1986. Gittler fue un hombre que llevó los números a niveles casi imposibles. Al igual que la de otros grandes científicos, una parte de su investigación lleva su nombre, los espectros Brown-Gittler. Para entender mejor estos espectros, hay que asomarse primero a la topología, pues es el tablero donde se juega esta ciencia. La topología estudia las propiedades cualitativas de los cuerpos geométricos y con la posibilidad de deformarlos sin problema, de manera que se puede obtener un círculo a partir de un triángulo para decir que estos dos son topológicamente equivalentes. La obra de Samuel Gittler dejó resultados teóricos que sirven en múltiples áreas como la química, la economía, en la capacidad de interpretar cálculos computacionales o en la robótica para resolver problemas de planeación motriz. Además, mantuvo altos estándares en la investigación matemática en México durante décadas y fue uno de los fundadores del Departamento de Matemática Matemáticas del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional, uno de los departamentos de matemáticas más importantes de América Latina.
Soy Diego Valadez, miembro del Colegio Nacional, donde tengo el privilegio de compartir la participación en esta formidable institución de la cultura mexicana con don Miguel León Portilla y con muchos otros eminentes protagonistas de la ciencia, del arte y de la cultura en general de México. Al rendir un homenaje al que me sumo gustoso a don Miguel León Portilla, estamos también reconociendo la trayectoria de un mexicano ejemplar que ha dedicado su vida al estudio de nuestra historia, pero además del pasado también se involucra en el presente, porque es un defensor de las culturas mexicanas, de la riqueza lingüística del país, de la exuberante producción que generaron las lenguas indígenas, y también es uno de los más fervorosos defensores de la propagación de los viejos valores de la filosofía mexicana que junto con nuestra literatura tradicional forman uno de los acervos culturales más importantes de nuestro país.
¿Cómo ha contribuido Miguel León Portilla a la cultura de México? Yo creo que ha hecho él solo, desde sus posiciones políticas, culturales, filosóficas sobre los pueblos originarios, ha logrado él solo más que muchísimas políticas lingüísticas de gobierno. Miguel tiene una obra multidisciplinaria porque su visión de los pueblos es multicultural, como debe ser cualquier pueblo. Miguel ha insistido una y otra vez en que las lenguas son patrimonios intangibles de los seres humanos y que cuando se pierde una lengua, se pierde un patrimonio para la humanidad. También ha hecho Miguel algo que es una reflexión profundísima sobre cómo fue el contacto, el encontronazo de la conquista. Y Miguel encontró, cuando era embajador en la UNESCO, encontró un eufemismo buenísimo, hay que decirlo, que fue encuentro de dos mundos. Me parece que él su impulso desechó un término muy desafortunado para la cultura, que es el descubrimiento de América, y lo llamó con un acertadísimo eufemismo, políticamente muy, muy acertado, y puso las aguas un poquito en calma en el año 92, Encuentro de dos mundos. Miguel tiene obra trascendente y profundísima sobre cómo se dio este encuentro. Y además es un hombre altamente ejecutivo, o sea, si él te dice esto hay que hacerlo y lo vamos a hacer así, Miguel León Portilla lo hace así. O sea, no solamente está en este mundo filosófico, en el discurso defensor de los pueblos indígenas, sino está en la ejecución de cómo hacer más visibles y darles respeto. Yo creo que ha contribuido a quitar una cantidad gigante de estereotipos que caían y recaen, por desgracia, todavía en los pueblos indígenas.
Quisiera destacar un aspecto de la enorme obra de don Miguel León Portilla, que es la que se relaciona con su defensa de los pueblos amerindios y de sus lenguas. Al paso de los años, don Miguel se ha convertido, diría yo, en el principal portavoz de la lucha de los pueblos amerindios y también de muchos lingüistas como yo, porque se respete la dignidad de estos pueblos, se respeten sus costumbres y se respeten sus lenguas. En ese sentido, el papel de don Miguel es invaluable. Donde quiera que uno se interese por saber qué hacer en favor de nuestras lenguas amerindias, siempre va a tener uno que consultar lo que ha escrito don Miguel León Portilla e incluso su actividad permanente. Quizás ahora no por su salud delicada, pero todos lo hemos visto participar activamente en esta promoción de los pueblos y de sus lenguas. Yo creo que es uno de los aspectos de don Miguel que van más allá del filólogo y el historiador que es, a un compromiso con nuestros pueblos amerindios.
Para mí y para todos los mexicanos, don Miguel León Portilla debe representar el mejor ejemplo de lo que es un hombre de cultura, un hombre que aprendió tanto como pudo de su entorno, que recogió la cultura pasada y presente de los mexicanos y que nos está dejando una herencia cultural absolutamente extraordinaria. A mí me impresionó cuando, siendo muy chico, estando en el bachillerato, leí La visión de los vencidos, y es una obra epopéyica absolutamente comparable a la Ilíada, una de las grandes tragedias de la historia de la humanidad. Pero probablemente el aspecto que a mí me conmueve más de don Miguel, aparte de tener la suerte de muchas veces sentarme a su lado y de sentirme un amigo de él, es el hecho de que para León Portilla los indígenas no son solamente parte de ese pasado excepcional que tuvimos, capaz de hacer pirámides o estatuas y piezas de jade y obsidiana, sino que para don Miguel León Portilla también los indígenas son ese grupo enorme de mexicanos que hemos marginado, que tienen una riqueza extraordinaria en términos culturales, en términos de conocimiento del ambiente, en términos lingüísticos, y para él no son solamente un vestigio del pasado, sino una realidad viva de México. Yo creo que uno de los grandes regalos que a mí me ha hecho el Colegio Nacional es la posibilidad de conocer y tratar a don Miguel y de haber recibido de mano suya la visión de los vencidos en náhuatl, que me parece la mejor demostración del compromiso de la cultura mexicana contemporánea con nuestro pasado y con ese otro componente del México que él se ha encargado de recuperar y llevar hacia la línea de primera.
Hola, soy Mardonio Caraballo, soy escritor, escribo en náhuatl y en castellano, Nixtlapaloa, Nochi Noixnimen, Nopatlen Tlemachtiani, tocan Miguel León Portilla. Hola, ¿cómo están? Bueno, envío un saludo al maestro Miguel León Portilla. Pienso que la obra del maestro ha sido fundamental para entender a México, sobre todo desde sus personas y sus habitantes anteriores, los que llegaron primero, como dirían los zapatistas, ¿no? Pienso que es fundamental su entendimiento para con aquellos hombres y mujeres de los cuales nos había contado una versión que en algún sentido dignificara, a su vez que acusara todo lo que había ocurrido en un tiempo. Creo que es importante, es un hombre de su tiempo, si bien pienso que la gran contribución de Miguel León Portilla sobrevive al tiempo, también pienso que ha acuñado de cuya agua han abrevado múltiples artistas, múltiples escritores.
Fano Manifolds. Thank you.
Gracias. Para empezar, quiero decir que estoy muy contenta de estar acá Y quiero agradecer a los organizadores, el comité científico, y ahora ya cambio al inglés. So today I want to tell you a little bit about Tsens Theorem. So this is a very classical theorem in algebraic geometry from the 30s. And then I will give a geometric interpretation of this very algebraic theorem and explain how this geometric interpretation is given us many ideas that are still being developed in algebraic geometry. So let me start by telling you so probably the simplest object that we study in algebraic geometry. So these are hypersurfaces in projective space. So we fix a field, for the moment this is any field, and we take a homogeneous polynomial of degree d and consider just the set of solutions of this polynomial equation. So this is a hypersurface in projective space. Now we want to understand how complicated this hypersurface is, and the complexity of this hypersurface will depend on several invariants or aspects. So to start, let's look at the degree. So intuitively, the biggest the degree is, the more complicated the hypersurface is. So let me just look at some examples, some simple examples. So let me look now inside CPN. So if I take a hypersurface of degree 1, so this is just a hyperplane, so this is just a CP n minus 1, and this is a very simple variety. This is just a projective space of dimension n minus 1. And let's look at the following problem. Let's consider the lines on this hypersurface. So in this case, for this hyperplane, if I fix any 2 points, x and y, I can always find a line that connects these 2 points. So in particular, what I'm saying is that a hyperplane is covered by lines. So this is a very simple statement. Now, if we start increasing the degree, so if we take, for instance, a hypersurface of degree 2 in CPN, so this is a quadric hypersurface. Now, if I take any point x, let's assume this is a smooth hypersurface. If I take any point and I look at all the lines that pass through this point, this is going to define a cone of codimension 1. So we still have many lines on these hypersurfaces. And now if we start increasing the degree, at some point we get to x, let me get this right, n minus 1 in P and CPN. And now here, if you take a general point x, there will be only finitely many lines through this point. So every time that I increase the degree by 1, I decrease the dimension of the cone of lines through a point by 1. And so until degree n minus 1, these hypersurfaces are always covered by lines. Now if I look at the next case, xn inside CPN, then this is no longer covered by lines. So through a general point, there is no line. But it is still covered by conics. And so let me just summarize what I've just said. So if I take a smooth hypersurface of degree d, then if d is at most n minus 1, it is covered by lines. And if the degree is at most n, then it's actually covered by conics. And if the degree is greater than n, then this hypersurface is no longer covered by lines or conics. As we will see soon, lines and conics are examples of what we call rational curves, and we will see that for degree greater than n, these varieties are not covered by rational curves. So we see that the complexity increases as we increase the degree. Now, let me also mention another point of view of the complexity of this variety also depends on the field K. So if we are for instance, over the complex or over any algebraically closed field, then this set is always non-empty, but this is no longer true for an arbitrary field. So if you take, for instance, the field of real numbers and you take a suitable quadratic polynomial, then this algebraic variety is going to be empty. So what Tsens theorem says is it gives conditions for existence of points on varieties for certain fields. So let me state Tsens theorem. So this was proved in 1936. So let's take as a field K a finite extension of the field of rational functions. If the degree of the hypersurface is less or equal than n, then the hypersurface is non-empty. There is always a point. So this is going to be the theorem that is going to inspire all the geometry that we are going to do from now on. So the first thing that I want to do is to reinterpret this statement from a geometric point of view. So so if you look at of the field CT, so this is the field, you can view it as the field of rational functions on a line. And more generally, if I take any finite extension of CT, this is the function field of a complex curve B. And now let's reinterpret Tsens theorem from this geometric point of view. So if I have a polynomial f, so this is the sum of ai, xi. So this is a polynomial, and my coefficients lie in this field K. So if I view this as a field of functions over a curve B, then if I take any point in my curve B, I can plug in B inside these coefficients. So these are functions on the curve, and I get a polynomial, let's say fb. Maybe I have to clear out the denominators here, but that's not important. And then once I plug in b here, what I get now is a polynomial with coefficients in C. So for every b, what I get is a hypersurface given by the zero set of this polynomial. So I can view my hypersurface ZF inside KPN, I can view it as a family of hypersurfaces parametrized by B. So I have X, so I view my X as now a family over B. So this is going to be contained in B cross CPN. And whenever I take a point B, the fiber is going to be, let me call XB, the zero set of this polynomial. So I view now the hypersurface can be viewed over, a hypersurface over this field K can be viewed as a family of hypersurfaces in projective space parametrized by B. And now, what does it mean to say that this hypersurface is non-empty? To say that it is non-empty, that means that we have a solution, let me call X, X naught to Xn, a solution of this polynomial. So each one of these entries, so these are elements in K. So that means that if I plug in B here, XB, is going to be now an element in the complex projective space, but it is a solution to this polynomial. So what I have is that I have for every B, I have a point in the complex projective space that lies inside this hypersurface. It is a solution of this polynomial. So the existence of a point is equivalent, so this point here is equivalent to the existence of a section of this morphism. So I will usually call this morphism pi, and the non-emptiness of the variety is equivalent to the existence of a section. So from now on, I want to look at Tsens Theorem from this point of view. So I will just restate it, and now we are going to work with this statement. So we have a complex algebraic curve. We have a family of hypersurfaces of degree d in complex projective space. And if the degree is less or equal than n, then pi admits a holomorphic section. Okay, so so now let's start to generalize this. So the first thing that we can do now is, instead of looking at a family of hypersurfaces over a curve, we can look at families of hypersurfaces over higher dimensional varieties. So this was done by Lang in 1952. So he gave the following generalization, and then this theorem now is known as Tseng-Lang's theorem. So if we now have a family of hypersurfaces of degree d, now parametrized by a base of dimension m, then we have a meromorphic section, provided that we have now this condition here on the degree. D to the m is less or equal than n. Okay, so, sorry? So here we could clear out denominators, but now when the base is greater than 2, then this can no longer be done. So we can extend it in codimension 1.
Is there a very simple example where this is obvious geometrically?
Yeah, well, yes. For instance, you can have P2 rational map to the blow up of P2 in one point. And well, it's not easy. It's not difficult to come up with examples. So this is a rational section is the best one can hope for in general. Okay, so now let me. Okay, so now what do I want to do? Now if you look at this statement from this point of view, what we have is we fix the dimension of the base, and now we want to find conditions on the fibers so that there exists a rational section. So the condition on the fiber that the theorem gives us is that the fiber is a hypersurface in projective space of degree satisfying this equation. And now the question is, so this is not an intrinsic condition on the fiber. This depends on the embedding. You asked that the fiber is embedded as a hypersurface of a certain degree. And so what we want to do is we would like to replace this condition by some geometric intrinsic condition on the fiber. So now I will state the problem that we are going to be addressing for the rest of this talk. So this is the problem that I want you to keep in mind. So we want to find intrinsic geometric conditions. So we are going to be fixing the base of the family, the dimension of the base, and we want to find some conditions. So this is going to depend, m is the dimension of the base. So we want to find some condition that we want to impose on the fibers, such that for hypersurface of degree d, this should be equivalent to the condition that appears in Tseng-Lang theorem. And we want the existence of, if the fibers satisfy this condition, we want to know that there are rational sections. So the theorem still holds for fibers satisfying this condition. Let me just make a very quick disclaimer here. So this is not quite true. There is some other ingredient that must be taken into account, which is called Brouwer obstruction. Whenever we have a fibration like this, we get an element in the Brouwer group of B, and if this element is non-zero, then there's then this is an obstruction to find in a section. So this is modulo Brouwer obstruction. But I will not, so this is not going to be important for this talk. Okay, so so let's look at a very special case. So let's look at the case, so this is the Tseng-Lang theorem, and let's look at the case where the dimension of the base is 1, so we are over a curve. And let's look at the case when n equals 2. So the fibers of the fibration are curves, plane curves of degree d. So in this case, what Tsens theorem requires for the existence of a section, if you look there, is d to the 1 is less or equal than 2. So this is what we have. So we have lines and conics. Now, what is special about lines and conics? So we have already seen them appearing here. And now let me tell you what is special about these curves. So plane curves, if you have a smooth plane curve in CP2, this is equivalent to having a compact Riemann surface. Now, compact Riemann surfaces are classified by their genus, and there is this natural trichotomy from the point of view, say, of universal coverings or curvature. There's a natural subdivision in these three classes. Now, if you give me a plane curve of degree d, how can I compute the genus of the curve? So this we learned this in the first course in algebraic geometry. This is the degree genus formula. So the degree of the curve, of the plane curve, and the genus are related by this. So we see that lines and conics are precisely those curves of genus 0. And so we can ask the natural question, well, could we replace, in our problem, can we replace the condition of having a fiber of hypersurface of degree at most 2 in CP2 by saying, if we have now a CP1 bundle, so genus 0 is the same thing as being abstractly a projective line, CP1. So if we have a CP1 bundle over a smooth curve, is it true that we can always find a section? And the answer is yes, but in fact, this was known way before Tsens Theorem. So this was a theorem by Neder and Enriquez in the 19th century. So we haven't really proved anything new, but I think at least it shows us that we are going in the right direction. And now the question is, how can we generalize to higher dimension this condition of being of genus 0? And so in higher dimension, this is done by what we call the canonical class of a variety. So let's start with a complex projective manifold. Then the anticanonical, let me define the anticanonical class first. This is just the first Chern class of the tangent bundle. So this is an element in the second cohomology group of X. And so that means that if I take some curve on X, so a curve on X, so this is a Riemann surface, so this gives me an element in the second, sorry, don't see this well. This gives me an element in the second homology group, so I can intersect it with the anticanonical class. And, well, geometrically, the number that I get, the integer that I get, is the average of the Ricci curvature of X along C. So this is not going to be important for the talk, but this is to say that the canonical class is measuring curvature. So it's something that measures the geometry of X. So, for instance, if you have a smooth projective curve, then the anticanonical class is just 2 minus 2g. And we can rephrase our trichotomy. Instead of in terms of the genus, we can rephrase it in terms of the sign of the canonical class. So we have negative canonical class. These are the curves of genus 0. Then 0 canonical class. So this is the curves of genus 1. And positive canonical class. Okay, so this is for curves. Now, in general, so the ones that appeared in Tsens Theorem are precisely the genus 0 ones, so the CP1. And so in general, the varieties where the canonical class has a negative definite sign are called Fano manifolds. So these are very important in birational geometry. So a complex projective manifold is Fano if its canonical class has a definite sign, so it intersects every curve with the same sign, and this sign is negative. So some remarks. Differently than the case of curves, if you give me a projective manifold, then in general the sign of the canonical class is not well defined. There will be some curves that intersected positively, others zero, other negatively. So this is not in general, does not have a very well-defined sign. However, so this is one of the biggest achievements of complex algebraic geometry in the last decades. So this is what is called the minimal model program, or the Mori program. So what it does is it gives it establishes, so this is a classification program in algebraic geometry, and it establishes that every projective manifold can be built up from varieties that have a definite sign of the canonical class, and there are these three classes. So these are the three building blocks of all projective varieties. So every projective variety can be built up from this one with some, algebraic geometric operations that you can put into them. So just a few remarks.
The pieces are only quasi-projective, or?
Okay, so maybe if you want a precise statement, let me give you a precise statement. So what the minimal program tells you is that after some well understood birational transformations, so you have your X, there are some well understood birational transformations that take it to another variety Y with a fibration to Y with a fibration to Z, such that, let's say, the Z now has negative canonical class. The fibers of the first fibration have zero canonical class, and the fibers of the second fibration have, the Z has positive canonical class. This one has fibers have zero canonical class, and fibers here have negative canonical class. So this is the upshot of the minimal model program. Now, in dimension 1, the minimal model program is just Riemann's classification of Riemann surfaces. In dimension 2, this was done by the Italian school. The classification was finished by the beginning of the 20th century. In dimension 3, this is much more complicated, and this program was finished by Mori in 1988, and it actually earned him the Fields Medal at that time. So this was, and more recently, in higher dimension, this is a very important theorem that was proved in some 10 years ago by Birk, Carcaccini, Haken, McKernan. And so this is really probably one of the most important developments in higher dimensional algebraic geometry in the last decade. Well, it's not completely done as in dimension 3, but it's good enough for most purposes that one is interested in. Okay, but this is not what I want to tell you, but this is just to say that studying Fano varieties is it's very natural from the point of view of birational geometry, given that these are one of the building blocks of projective manifolds. Now, okay, let's go back to the problem that we are interested in. We want to find intrinsic conditions. Now, let's just look at the problem for R1. So this is the original Tsens Theorem when we have a fibration over a curve. So we have that we want to find conditions such that for hypersurface, the condition is equivalent of the condition that appears in Tsens Theorem, so the degree less or equal than n. And we want the Tsens theorems to hold, meaning the existence of a section when the fibers of the fibration satisfy this condition. And then from what I was just telling you, a natural question is, can we take the condition R1 to be X is Fano? So Fano would be the generalization of rational curves of degrees of genus zero curves to higher dimensions. And then, okay, so let's check. So for hypersurfaces, computing the canonical class is very easy. So for hypersurfaces, the sign of the canonical class is well defined, and the sign is exactly the sign of d minus n minus 1. So if you compute, you see that negative canonical class corresponds precisely to d less or equal than n. And so this is the first thing that we have to check. And then, so this is easy. This is just really simple computation. This is called the canonical formula, the adjunction formula. And now to prove the existence of a section for families of Fano varieties, this is a much harder problem, but it was solved positively by Graeber, Harris, and Starr in 2003. So they show that if you have a family of Fano varieties parametrized by a one-dimensional base, then you always have a section. Okay, so now we can, of course, ask, can we do better than that? I mean, can we, imposing that a variety is Fano, this is a very strong condition, can we put some weaker condition, can we take some weaker condition to be R1? And in fact, we can, and let me describe a special property of Fano manifolds. So Fano manifolds contain many rational curves. So we have already seen this for hypersurfaces. We saw that for degree at most n, they're covered by lines and conics. And now, more generally, it's a theorem of Campana and Colamia Okamori. So this is an old theorem that says that Fano manifolds are rationally connected. So what does this mean? Rationally connected means that if you take two general points in the variety, you can find a rational curve that connects them. Just like here, any 2 points can be connected by a line. Well, in a quadric, not any 2 points can be connected by a line, but they can be connected by a conic, and so on. And then, let me point out, and this is something that I mentioned for hypersurface, that on the other side, projective manifolds with non-negative canonical class, then they do not contain any rational curve through a general point. So this condition really differentiates like these classes of varieties. And actually what Graeber, Harris, and Starr proved, and this is the original statement of their theorem, is that we can take the condition R1 to be rationally connected, being rationally connected. So if you have a family of rationally connected varieties parametrized by a curve, you can always find a section. They proved something else. They proved that this is the best you can do. So this is the weakest condition that you can put on the fibers to have a general statement like this. Okay, so now the problem is completely solved for one-dimensional base, and now we would like to do the same thing for higher dimensional base. Okay, so sorry, let me just see how I'm doing. Okay. So now we move to higher dimensions and things get much more complicated. And as we will see, the problem is still wide open and it's not clear what the best answer would be. And so before I start explaining some of the results that we have, let us now pause here and get some inspiration from topology. So what would be the analogous statement in topology? So suppose we have, so this would be the analogous statement. We have a family of fibration of CW complexes. I will denote the typical fiber by F, and this family is parametrized by a base of dimension M. And we want to know when there is a continuous section. But in topology, this problem is completely solved. In topology, this problem is completely solved. And the answer is if we can find a section provided that the typical fiber F is M-1 connected. let me remind you the definition of K-connectedness. So let's take a topological space F, and let's fix a point in this topological space. We can look at the loop space of X at the point P. So this is, as a set, these are all the loops based at the point. Then we can there is a topology that we can put in this space so that this itself becomes a topological space. So this is the open compact topology. So if we put this topology, then we can define the homotopy groups of F in a recursive way as being the kth. So the zero homotopy is just, well, this is just a set for k equals 0. This is just the set of path-connected components. And as soon as k is 1, this has a structure of a group. So the pi 1 is just the fundamental group of the space. And in general, the pi k of F is defined to be the pi k minus 1 of the loop space with this natural topology. And we say that F is k-connected if all the homotopy groups up to k vanish. Now, so let's see what it tells us for our original problem. So let's assume that we have a family of CW complexes over a one-dimensional base. And what the theorem, what the statement says is that if F is zero connected, meaning path connected, then we can find a section. Now, if we want to find sections over surfaces or over two-dimensional bases, then the requirement is that F is one connected, which is just to say that it is connected and it has trivial fundamental groups. So this is simply connected. So let's just look at these two cases. And now, since we know how to solve the problem in topology, let's try and make an analogy. Let's go through the proof in topology and see if we can imitate it in algebraic geometry. So now let's make a bridge from topology to algebraic geometry. So a topological space, whenever we have a topological space, we will take X to be a projective variety. Now the interval 0, 1, which parameterizes the paths, are going to be replaced by CP1, a rational curve. Now, let's look at the condition when m equals 1, the solution in the topology was that we require that the fibers of the fibration are path connected. And notice that if you translate, path connected means that any 2 points can be connected by a path. In algebraic geometry, this would translate to any 2 points of the projective variety can be connected by a rational curve. So this is being rationally connected. And this is exactly the solution that we get in algebraic geometry. So the point that I want to make here is that if you use this dictionary that I put there, then the two solutions in the topology and the one in algebraic geometry for one-dimensional base are equivalent, are analogous. So let's try to do the same thing for the next case that we don't know, for which we don't know the answer, which is m equals to 2. So the solution of the topology problem is X. We want to require that in order to get a section over a two-dimensional base, we require that the fibers are simply connected. That means that X is path connected and the loop space is path connected. Now let's see how this would translate to algebraic geometry. So X is simply connected, X path connected, as we've seen, is just X is rationally connected. And now, what about the loop space being path connected? So now we have to do something here. So what would be the loop space analog in algebraic geometry? So the loop space, so in topology, is just the topological space consists of paths based at one point. So if we use this dictionary, we would look at this space of rational curves that pass through one point. Now, there is a problem here because in topology, we gave a structure of topological space to this loop space. Now, if you consider the space of all rational curves through a point, well, this exists as a scheme. But if we want to go, we cannot give it a structure of projective variety. For instance, if you have rational curves, even in CPN, rational curves have different degrees, and rational curves of different degrees will lie in different components. So this is not irreducible, and so there's no way that you can require that this is path connected. And moreover, these components in general are not projective. For instance, if you look at the space of rational curves, they can degenerate into, say, trees of rational curves. So this is not a good space to look at. However, let me just give you an alternative for this loop space in algebraic geometry. So this would be the following. If I have my algebraic variety, I can fix a point, P, and I can look at the rational curves of minimal degree through this point. So for instance, in this case here, in these cases, if I fix a point, I would look at the space of all the lines that pass through this point. Well, in this case here, I would have to look at the space of all the conics that pass through this point. So because of this minimality of the degree, this, let me call it loop variety, or variety, in general we call it the variety of minimal rational curves. So this has a natural structure of a projective variety. And now we could try and ask if, well, then we should ask that this loop variety is itself rationally connected. So this would be the simple translation from topology to algebraic geometry. Well, however, okay, now I should say that this is just an inspiration. There is no way that we can make it work in general. And let me just state, if you go through the proof of the topological statement, then you will notice that one thing that we use in topology is that we're putting some condition on the loop space, but when you want to construct the sections, you actually have to look at of paths connecting 2 points, P and Q. However, these are homotopy equivalent, so you can just compose a loop with a fixed path connecting 2 points, and then you get equivalent spaces. So in topology, once you know that one is, say, path connected, then the other one is going to be path connected as well. However, in algebraic geometry, if you look at the spaces of rational curves through 2 points, say of minimal degree, this can be very different than the space of rational curves passing through 1 point. And it's very difficult to get information from one, from the loop space to the space of curves through 2 points. So this is something that we don't know in general how to do, how to go from properties of this variety to properties of this variety. So this this part of the proof breaks down completely. So, okay, but however, there has been work on that. So the Young and Starr, they propose, well, I put this unstable definition. They propose several definitions of what they call rationally simply connected varieties. So I call it unstable because they have many papers about this, and their definition vary from paper to paper depending on what they want to prove. So, I mean, they have some common features. So the common features is that, well, they always require that the variety itself is rationally connected, that the space of minimal rational curves through a point, again, is rationally connected, and then they often require some version of the spaces of curves through 2 points to be rationally connected. And this part here varies, so what version they use depends on the statement and on the context, and some technical conditions that I would not even dare to try to define. So this is This is something that really appears, it's a very technical condition that appears in the deformation theory when you want to work with these varieties. And so I just put them some technical conditions, but these seem to be key. These technical conditions, they actually appear in all of the definitions. And let me just say something, let me just go back one slide to say that this technical condition is what they use from information on this to go to this, to geometric information on this. But okay, I don't want to say much about this. And what they, and let me remind you, the problem that we want to prove, to solve, we want to find conditions that would replace the degree condition in Tsen's lung. So now we are going, if you want to do it for R2, what they ask is that, can one take R2 to be X is rationally simply connected? So this is already a difficult question because there is no definition of rationally simply connected, but still they do prove that they verify this for hypersurfaces for one definition of rationally simply connectedness, and they prove in some very special cases existence of section with a different definition, non-equivalent definition of rationally simply connected. So it seems that there is something there. However, it's still not clear what the right definition should be. And so instead of trying to go in this direction, what I have been doing together with Ana Maria Castravet is trying to go to a different path. So remember that the rationally connected condition was a generalization of the Fano condition. So instead of trying to define what would be the ultimate solution, let's try to find some simpler solution that has some natural statement. And so we have introduced, so de Jong and Starr had already introduced this for m equals to 2, and we introduced and studied it in the general case. We say that a complex projective manifold is M Fano. So remember, Fano meant that the first Chern class of the tangent bundle was positive. And now M Fano, we require that all the Chern characters of the tangent bundle are positive for all I between 1 and M. So this is what we call a Fano, and what we ask is that this is much stronger than require any of these conditions of simply rational connectedness. But can we take Rm to be X is M Fano? So this would be maybe not the ultimate, but this would be a suitable, nice geometric solution to the problem. And the first thing that we have to do is to check it for hypersurface. And again, for hypersurfaces, computing these Chern characters is very easy. And if you compute this, you get that for hypersurface of degree D, this M Fano condition is exactly the degree condition that we see in Lang's theorem. So for hypersurfaces, to check that for hypersurfaces we get what we want, this is very easy. And now, of course, we want to prove the existence of sections. So this seems to be a very hard problem, and I think that we are still very far away from it. But what we started to do is then to study the geometry of these M Fano varieties. And so we conjecture, so this is a bit inspired again by the topology, the problem in topology, and this recursive definition of homotopy groups. We conjecture that if X is M Fano, then the loop space, the space of rational curves of minimal degree, should be M minus 1 Fano. And we've been working on this conjecture since then. And so let me tell you what we could prove. So we could prove this for, say, M at most 3. So let me just tell you. Let me just tell you how we prove this, and I have to say that this is the Latin American Colloquium of Algebra, and I was feeling a bit uneasy that there's not much algebra in my talk. There was Tsen's original theorem, and then I just moved to geometry. So I decided to just put a formula just to say that we actually do. We do some algebra. So let me just tell you how we prove this. So when we have this, so we have our variety X, and we are fixing this point P. And we consider this what I'm calling loop space. These are the rational curves of minimal degree through P. So what does that mean? So if you have a rational curve of minimal degree through P, let's call it C, then this is parameterized by a point in this loop space. And over this loop space, I have a universal family. So I have, say, a P1 bundle. So this is a P1 bundle over let me call this pi, with an evaluation morphism. So over a fiber over the point corresponding to C is a P1 that is mapped exactly to C under the evaluation map. So we have this diagram, and then what we can do is if you have a cohomology class on X, we can pull it back to the universal family, push it forward, and again we get some class of the appropriate degree on the space of loops. And then by using, say, growth and decrement ROC, we actually compute all the Chern characters of this loop space in terms of, so let's see what appears in this form. I don't want, this is not important, but see, what I want to show is that the Chern characters of the loop space, they can be computed from the Chern characters of X, the original variety. So this L is some natural polarization that one can put here on this loop space. And these Bj's are the Bernoulli numbers. So what you see from this formula is that there are some plus and minus signs. So it's easy to see that pulling back and pushing forward preserves the sign of the Chern characters, but there are all this minus, plus and minus signs, and it's very difficult to control the sign in this formula. And so for m at most 3, we can sometimes rewrite the formula and use some geometric properties to be able to show that the corresponding Chern characters of the loop space are still positive. And in general, it's not easy. Sorry? So in general, it's not easy to control these signs. But however, there has been some recent developments. So if the conjecture is true, so let's assume that the conjecture is true, then recursively we could look at the loop space based at some point of this loop variety, and so on. And so if this is true, then we take loop space m times, and we would get something Fano. So this was proved recently by this Japanese mathematicians, Suzuki and Nagaoka. So they proved so they had to put that this technical condition here that seems to be very difficult to verify in general, to check in general. They prove that if X is m Fano, then if you take the loop space of the loop space of the loop space m times, then this is Fano. So this would be a consequence of this conjecture. And let me just say that this is actually a very hard problem. So in general, if you have an m Fano variety, so we've been investigating the geometry of these varieties. It's very difficult even to guarantee the existence of a positive dimensional family of rational curves of minimal degree. And in order to get this, they have to assume that the dimension of this space is very, very, very big. So we don't know how to verify, to prove that this holds starting from this condition. So this is still very mysterious. These are very mysterious varieties. So let me just, let me see how much time I have. Okay, so let me just finish. Let me just go back to this. So this problem that I mentioned when we have that in topology, these are sort of homotopy equivalent spaces, while in algebraic geometry, these are very different. And if we want to prove existence of sections, say, over surfaces, we have to control not only this space, and this would be controlled by this conjecture. So once we know that this holds, then automatically we get rationally connectedness. But we cannot, in general, this does not say anything about this space. So what a student of mine has done in his PhD thesis is to consider the case when X is conic connected. So in general, so I take my variety is conic. A variety is conic connected if any 2 points can be connected by a conic. And if, in addition, it is true Fano, what we proved is that this space of conics through 2 points is Fano. And here, this is a projective space because we also allow for degenerate conics, the unions of 2 lines or double lines. So this is a projective variety, and we prove, again, by writing a more complicated diagram and using Grothendieck, increment rock, and comparing the Chern characters, we can prove this statement. But in general, very, very little is known from this variety. And let me just state, so there are many conjectures, but let me just state a very simple conjecture that seems very natural, but we don't know how to answer, which is a conjectural characterization of projective space. So if you take a projective space, CPN, and you compute all the Chern characters from 1 to n, these are all positive. And we conjecture that if you have an n-dimensional variety, which is n-Fano, meaning all the Chern characters up to degree n are all positive, then this has to be Pn. I mean, this has to be true, although we don't know how to prove it. But okay, so this is what I wanted to tell you today, and thank you for your attention.
Questions?
So, I'm sorry. The unstable definition of Johannes and Jason, does it satisfy this recursive condition that if it's rationally simply connected for M, then the loop space is also rationally simply connected?
Sorry?
Does it satisfy the recursive definition that you want your M-Fano definition to satisfy, that if you have a variety that is rationally simply connected for M, then the loop space of that guy, with their definition, their unstable definition, is also rationally simply connected?
So if you have a rationally simply connected, then the loop space is going to be rationally connected. Yeah. Yes. So this is part of the definition. So they put it as part of the definition.
But I thought it was only for the I thought it was only for the first step. So if you continue further.
Okay. So yes, let me go back to the unstable definition here. So they require that both X and the loop is rationally connected. They also require some version of these rational curves through 2 points being rationally connected. And this technical condition here is something that allows you to do deformation theory, and then from these conditions, roughly speaking, verify that the minimal rational curves through any number of points are rationally connected. So this is what this technical condition is for doing this deformation theory on surfaces.
Can you say a word about the Brouwer class, the Brouwer obstruction that appears? It's in two variables.
Okay, so if you look at this, the general problem to find a section, then what you would hope if you would hope we would hope, for instance, that if you have any Pn bundle over, say, a surface, this should have a section, because Pn is n Fano. However, there are examples of projective space bundle over, say, 1 billion varieties that do not have a rational section. And so the Brouwer obstruction tells you exactly when and having a section, well, it's not the same, but you can think of, so this having a section should be sort of, you can think of this as coming from the projectivization of a global vector bundle. And what the Brouwer obstruction tells you is exactly when a projective space bundle is not the projectivization of a vector bundle.
But it's an element in the Brouwer group of this...
Of the base.
Of the base.
Yes. And so in general, so you can, for instance, if you have a projective space bundle with a global O1, something that restricts, a line bond that restricts to O1 to the fibers, then the Brouwer obstruction is 0 in this case, which is exactly saying that it comes from a vector bundle.
More questions?
In the first theorem you stated about surfaces of degree n-1, and you say that there is only finitely many curves going through each point, yes, but it is still rationally connected.
It's still rational.
So it means that if you take two generic points, you need a certain number of rational curves to connect them.
Right.
But is there a uniform bound on the number of curves you need?
Yes, there is. You can find a bound. The known bounds are not optimal, but one can find, because what you do is you can look. You start with a point, and then look at all the points that can be connected to it by a line, and then you look at all the points that can be connected to this locus by a line, and then you always increase this by at least, say, 1, and then eventually you connect 2 points by these chains of rational curves. And so the bound on the number of rational curves, of lines that you need, can be easily computed, although it may not be optimal, and this chain of lines can be smoothed to a rational curve. So there are bounds in general. So for me, this is a very interesting question. I looked at this also in my PhD thesis to try to get better bounds to the minimal degree of the rational curves that connect 2 points in a rationally connected variety. But there is still, so in general, I don't think there is an optimal bound.
More questions? Thanks a lot.
Samuel Hitler fue ingeniero civil, matemático y miembro del Colegio Nacional desde 1986. Hitler fue un hombre que llevó los números a niveles casi imposibles. Al igual que la de otros grandes científicos, una parte de su investigación lleva su nombre, los espectros Brown-Kittler. Para entender mejor estos espectros, hay que asomarse primero a la topología, pues es el tablero donde se juega esta ciencia. La topología estudia las propiedades cualitativas de los cuerpos geométricos y con la posibilidad de deformarlos sin problema, de manera que se puede obtener un círculo a partir de un triángulo para decir que estos dos son topológicamente equivalentes. La obra de Samuel Gittler dejó resultados teóricos que sirven en múltiples áreas como la química, la economía, en la capacidad de interpretar cálculos computacionales o en la robótica para resolver problemas de planeación motriz. Además, mantuvo altos estándares en la investigación matemática en México durante décadas y fue uno de los fundadores del Departamento de Matemáticas del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional, uno de los departamentos de matemáticas más importantes de América Latina.
Soy Diego Valadez, miembro del Colegio Nacional, donde tengo el privilegio de compartir la participación en esta formidable institución de la cultura mexicana con don Miguel León Portilla y con muchos otros eminentes protagonistas de la ciencia, del arte y de la cultura en general de México. Al rendir un homenaje al que me sumo gustoso a don Miguel León Portilla, estamos también reconociendo la trayectoria de un mexicano ejemplar que ha dedicado su vida al estudio de nuestra historia, pero además del pasado, también se involucra en el presente, porque es un defensor de las culturas mexicanas, de la riqueza lingüística del país, de la exuberante producción que generaron las lenguas indígenas, y también es uno de los más fervorosos defensores de la propagación de los viejos valores de la filosofía mexicana que junto con nuestra literatura tradicional forman uno de los acervos culturales más importantes de nuestro país.
¿Cómo ha contribuido Miguel León Portilla a la cultura de México? Yo creo que ha hecho él solo, desde sus posiciones políticas, culturales, filosóficas sobre los pueblos originarios, ha logrado él solo más que muchísimas políticas lingüísticas de gobierno. Miguel tiene una obra multidisciplinaria porque su visión de los pueblos es multicultural, como debe ser cualquier pueblo. Miguel ha insistido una y otra vez en que las lenguas son patrimonios intangibles de los seres humanos y que cuando se pierde una lengua, se pierde un patrimonio para la humanidad. También ha hecho Miguel algo que es una reflexión profundísima sobre cómo fue el contacto, el encontronazo de la conquista. Y Miguel encontró, cuando era embajador en la UNESCO, encontró un eufemismo buenísimo, hay que decirlo, que fue encuentro de dos mundos. Me parece que él su impulso desechó un término muy desafortunado para la cultura, que es el descubrimiento de América, y lo llamó con un acertadísimo eufemismo, políticamente muy, muy acertado, y puso las aguas un poquito en calma en el año 92, Encuentro de dos mundos. Miguel tiene obra trascendente y profundísima sobre cómo se dio este encuentro. Y además es un hombre altamente ejecutivo, o sea, si él te dice esto hay que hacerlo y lo vamos a hacer así, Miguel León Portilla lo hace así. O sea, no solamente está en este mundo filosófico, en el discurso defensor de los pueblos indígenas, sino está en la ejecución de cómo hacer más visibles y darles respeto. Yo creo que ha contribuido a quitar una cantidad gigante de estereotipos que caían y recaen, por desgracia, todavía en los pueblos indígenas.
Quisiera destacar un aspecto de la enorme obra de don Miguel León Portilla, que es la que se relaciona con su defensa de los pueblos amerindios y de sus lenguas. Al paso de los años, don Miguel se ha convertido, diría yo, en el principal portavoz de la lucha de los pueblos amerindios y también de muchos lingüistas como yo, porque se respete la dignidad de estos pueblos, se respeten sus costumbres y se respeten sus lenguas. En ese sentido, el papel de don Miguel es invaluable. Donde quiera que uno se interese por saber qué hacer en favor de nuestras lenguas amerindias, siempre va a tener uno que consultar lo que ha escrito don Miguel León Portilla e incluso su actividad permanente. Quizás ahora no por su salud delicada, pero todos lo hemos visto participar activamente en esta promoción de los pueblos y de sus lenguas. Yo creo que es uno de los aspectos de don Miguel que van más allá del filólogo y el historiador que es, a un compromiso con nuestros pueblos amerindios.
Para mí y para todos los mexicanos, don Miguel León Portilla debe representar el mejor ejemplo de lo que es un hombre de cultura, un hombre que aprendió tanto como pudo de su entorno, que recogió la cultura pasada y presente de los mexicanos y que nos está dejando una herencia cultural absolutamente extraordinaria. A mí me impresionó cuando, siendo muy chico, estando en el bachillerato, leí La visión de los vencidos, y es una obra epopéyica absolutamente comparable a la Ilíada, una de las grandes tragedias de la historia de la humanidad. Pero probablemente el aspecto que a mí me conmueve más de don Miguel, aparte de tener la suerte de muchas veces sentarme a su lado y de sentirme un amigo de él, es el hecho de que para León Portilla los indígenas no son solamente parte de ese pasado excepcional que tuvimos, capaz de hacer pirámides o estatuas y piezas de jade y obsidiana, sino que para don Miguel León Portilla también los indígenas son ese grupo enorme de mexicanos que hemos marginado, que tienen una riqueza extraordinaria en términos culturales, en términos de conocimiento del ambiente, en términos lingüísticos, y para él no son solamente un vestigio del pasado, sino una realidad viva de México. Yo creo que uno de los grandes regalos que a mí me ha hecho el Colegio Nacional es la posibilidad de conocer y tratar a don Miguel y de haber recibido de mano suya la visión de los vencidos en náhuatl, que me parece la mejor demostración del compromiso de la cultura mexicana contemporánea con nuestro pasado y con ese otro componente del México que él se ha encargado de recuperar y llevar hacia la línea de primera.
Hola, soy Mardonio Caraballo, soy escritor, escribo en náhuatl y en castellano, Nixtlapaloa, Nochi Noixnimen, Nopatlentle Machtiani, tocan Miguel León Portilla. Hola, ¿cómo están? Bueno, envío un saludo al maestro Miguel León Portilla. Pienso que la obra de el maestro ha sido fundamental para entender a México, sobre todo desde sus personas y sus habitantes anteriores, los que llegaron primero, como dirían los zapatistas, ¿no? Pienso que es fundamental su entendimiento para con aquellos hombres y mujeres de los cuales nos había contado una versión que en algún sentido dignificara, a su vez que acusara todo lo que había ocurrido en un tiempo. Creo que es importante, es un hombre de su tiempo, si bien pienso que la gran contribución de Miguel León Portilla sobrevive al tiempo, también pienso que ha acuñado de cuya agua han abrevado múltiples artistas, múltiples escritores, ahora en lenguas originarias, que sin duda están haciendo una revolución con respecto de quiénes son, con respecto de la identidad, con respecto de México, quiénes somos los mexicanos, por qué somos como somos y por qué nos vemos como nos vemos. Y pienso que todas esas reflexiones no podrían haberse dado si no hubiese un inicio, y pienso que en ese sentido, en la historia, para entender la historia que tenemos ahora, para comprender a los pueblos indígenas en la narrativa nacional, me parece fundamental el agua, digamos, el abrevadero que se llama Miguel León Portilla.
Hola, ¿qué tal? Soy Juan Villoro, escritor y periodista, y me da mucho gusto poder hacer una evocación de Miguel León Portilla, uno de los grandes intelectuales de México, que ha sido un intercesor extraordinario entre la cultura y la lengua de los pueblos originarios, principalmente del náhuatl y nosotros. Miguel León Portilla ha sido ese intermediario esencial entre un mundo desaparecido, derrotado, de los primeros mexicanos, que es el mundo de la visión de los vencidos, pero que todavía perdura entre nosotros, perdura sin una voz propia que se escuche, y que gracias a intercesores como Miguel León Portilla puede ser reconocido. Entonces ha sido valiosísimo este trabajo de entender la importancia, el significado del legado indígena. Ahora bien, creo que el gran legado de León Portilla tiene que ver con el pasado, pero también con el futuro. Él apunta a una cultura que ha sido sojuzgada, destruida, pero que puede ser todavía rescatada y puede perdurar entre nosotros, pero creo que implícitamente también está señalando a un futuro. ¿Cómo seremos los mexicanos del porvenir? Y yo creo que ahí esta figura puente nos está diciendo la verdadera historia de los pueblos originarios será escrita en su lengua o en sus muchas lenguas, y será escrita por ellos mismos. Llegará un momento en que México no tendrá necesidad de intermediarios, de intercesores para conocer esa cultura, porque esa cultura volverá a estar viva entre nosotros. De modo que creo que el gran legado de Miguel León Portilla tiene que ver con la recuperación de un pasado, pero también con el señalamiento de que hay una aventura por venir, que es la de que los propios pueblos escriban su historia en la lengua que él ha traído hasta nosotros.
Marcos Moszyński-Borodiański fue físico y miembro del Colegio Nacional desde 1972. Moszyński continuó su labor en la UNAM con la búsqueda de las propiedades del oscilador armónico. Un sistema físico tiene simetría porque después de transformarse queda invariante. Por ejemplo, después de que una esfera gira sobre alguno de sus ejes, su forma es exactamente igual antes y después de la rotación. Este concepto fue aplicado por Moszyński para explicar las estructuras del núcleo atómico en un oscilador armónico. ¿Y qué es un oscilador armónico? El oscilador se asemeja al comportamiento de un resorte que cuando se le intenta estirar, tiende a regresar a su estado normal y comienza a oscilar. Moszyński logró simplificar los cálculos en estructura nuclear usando los que él llamó paréntesis de transformación. Sus estudios llegaron a tal fama que la comunidad científica se refería a ellos como los Moszyński brackets. Moszyński no solo se convirtió en referencia mundial, sino que ha dejado un legado en las ciencias exactas. Ahora, como homenaje a su carrera científica, la Fundación Marcos Moschinsky continúa con sus ideales otorgando las cátedras que llevan su nombre. Este es un programa anual que impulsa la trayectoria y proyectos de investigación de jóvenes científicos mexicanos en las áreas de física, matemáticas y las ciencias químico-biológicas. Químico-biológicas.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del ciclo.
Diálogos a través del tiempo.
Alejandro Frank es físico y se integró al Colegio Nacional en el 2016. Frank ha desarrollado trabajos en la mecánica cuántica y es pionero y fundador en la teoría algebraica de la dispersión. Para Alejandro, la dispersión algebraica es una metodología matemática para describir la interacción entre las partículas. En mecánica cuántica hay un principio que no permite saber con qué velocidad se está moviendo un sistema, pero sí saber dónde está, o al revés, saber su velocidad, pero no su ubicación. Pero Frank desarrolló un método para saber ambos, la velocidad y la posición. Lo logró analizando un sistema en su transición de fase. Para este tipo de análisis se necesitan modelos teóricos muy complejos. Frank describe a la mecánica cuántica como una técnica matemática especialmente capaz de describir a la naturaleza, y sus investigaciones sobre la teoría algebraica de la dispersión las aplicó en este campo. Octavio Novaro Peñalosa fue físico y miembro del Colegio Nacional desde 1995. Una de las ramas que más le debe a Novaro es la industria petroquímica por sus estudios sobre fuerzas intermoleculares y catálisis teórica. Los catalizadores son partículas muy pequeñas de metales preciosos y Novaro los describía como piedras más pequeñas que las aspirinas con el poder de acelerar las interacciones entre las moléculas del hidrocarburo. Y el resultado era genial, reacciones químicas en menor tiempo, lo que implicaba usar menos energía y menos recursos. Sucede que una vez extraída la materia prima de los pozos petroleros y después de que se reservan en plantas colosales, se deben calentar a muy altas temperaturas para lograr su reacción. Y para acelerar este proceso se les agrega una dosis de catalizadores. Después de la expropiación de Lázaro Cárdenas, México estaba obligado a desarrollar métodos propios que no dependieran de una concesión extranjera para obtener productos derivados del petróleo a menor tiempo y menor coste. Samuel Gittler fue ingeniero civil, matemático y miembro del Colegio Nacional desde 1986. Gittler fue un hombre que llevó los números a niveles casi imposibles. Al igual que la de otros grandes científicos, una parte de su investigación lleva su nombre, los espectros Brown-Gittler. Para entender mejor estos espectros, hay que asomarse primero a la topología, pues es el tablero donde se juega esta ciencia. La topología estudia las propiedades cualitativas de los cuerpos geométricos y con la posibilidad de deformarlos sin problema, de manera que se puede obtener un círculo a partir de un triángulo para decir que estos dos son topológicamente equivalentes. La obra de Samuel Gittler dejó resultados teóricos que sirven en múltiples áreas como la química, la economía, en la capacidad de interpretar cálculos computacionales o en la robótica para resolver problemas de planeación motriz. Además, mantuvo altos estándares en la investigación matemática en México durante décadas y fue uno de los fundadores del Departamento de Matemáticas del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional, uno de los departamentos de matemáticas más importantes de América Latina.
Soy Diego Valadez, miembro del Colegio Nacional, donde tengo el privilegio de compartir la participación en esta formidable institución de la cultura mexicana con don Miguel León Portilla y con muchos otros eminentes protagonistas de la ciencia, del arte y de la cultura en general de México. Al rendir un homenaje al que me sumo gustoso a don Miguel León Portilla, estamos también reconociendo la trayectoria de un mexicano ejemplar que ha dedicado su vida al estudio de nuestra historia, pero además del pasado, también se involucra en el presente, porque es un defensor de las culturas mexicanas, de la riqueza lingüística del país, de la exuberante producción que generaron las lenguas indígenas y también es uno de los más fervorosos defensores de la propagación de los viejos valores de la filosofía mexicana que junto con nuestra literatura tradicional forman uno de los acervos culturales más importantes de nuestro país.
¿Cómo ha contribuido Miguel León Portilla a la cultura de México? Yo creo que ha hecho él solo desde sus posiciones políticas, culturales, filosóficas sobre los pueblos originarios, ha logrado él solo más que muchísimas políticas lingüísticas de gobierno. Miguel tiene una obra multidisciplinaria porque su visión de los pueblos es multicultural, como debe ser cualquier pueblo. Miguel ha insistido una y otra vez en que las lenguas son patrimonios intangibles de los seres humanos y que cuando se pierde una lengua, se pierde un patrimonio para la humanidad. También ha hecho Miguel algo que es una reflexión profundísima sobre cómo fue el contacto, el encontronazo de la conquista, y Miguel encontró, cuando era embajador en la UNESCO, encontró un eufemismo buenísimo, hay que decirlo, que fue encuentro de dos mundos. Me parece que él su impulso desechó un término muy desafortunado para la cultura, que es el descubrimiento de América, y lo llamó con un acertadísimo eufemismo, políticamente muy, muy acertado, y puso las aguas un poquito en calma en el año 92, Encuentro de dos mundos. Miguel tiene obra trascendente y profundísima sobre cómo se dio este encuentro. Y además es un hombre altamente ejecutivo, o sea, si él te dice esto hay que hacerlo y lo vamos a hacer así, Miguel León Portilla lo hace así. O sea, no solamente está en este mundo filosófico, en el discurso defensor de los pueblos indígenas, sino está
So first, just to remind you that it's a good idea to pay for the dinner if you want to go to the dinner. That's with me. Also, I still have some SIM cards for the internet. If you need them, just ask me. They cost nothing. And well, the second talk of today is Centralizers in Profinite Groups by Pavel Shumyatsky from the University of Brasilia.
Thank you. Well, so I'll be speaking about centralizers, but I'd like to start by saying thanks to the organizers for organizing this colloquium, and in particular for inviting me to give a talk here. So centralizers are one of the most important concepts in algebra. Oops. One could even say centralizers are a central concept in algebra. In particular, in the theory of finite groups, centralizers played really a crucial role in shaping up the theory as we know it now. One of such famous seminal results on centralizers in finite groups is the theorem of Brouwer-Fowler that they proved several results on centralizers, and in particular they proved that a finite simple group that has an involution with centralizer of order at most m has order bounded by a function of m only. And so this later motivated a lot of work in classification of finite simple groups, since this suggested the idea of that the finite simple groups can be classified just according to centralizers of involutions. Then eventually that idea didn't work quite in that way, but anyway this theorem had huge inspirational impact, and that the work on classification of finite simple groups was started with this theorem. Another famous topic that really had huge importance in the theory of finite groups is the study of groups with abelian centralizers, so-called CA groups. It's easy to understand that in such groups, the commutativity is a transitive relation in the sense that if x commutes with y and y commutes with z, then x also commutes with z. So because of this, such groups also called CT groups. So there is a classification of all finite groups with this property. This happen to be all very small groups, either abelian or Frobenius groups with some specific properties, or the simple groups PSL2 over a finite field in characteristic 2. And only these groups. But maybe even more important, what is not explicitly in this classification, Suzuki proved that any CA group of odd order is soluble. And then ideas of Suzuki were used by Feite and Thomson in their famous theorem that every group of odd order is soluble. And that, of course, had a profound effect on the whole theory. Now, any result about finite groups has certain impact on infinite groups. And especially this impact is strong if we deal with so-called locally finite or profinite groups. I just recall that locally finite groups are groups in which all finitely generated subgroups are finite. These are infinite groups, but they inherit a lot of properties of finite groups. And this also groups can be also defined as direct limits of finite groups. Now, profinite groups are inverse limits of finite groups, and so there is some natural duality between locally finite and profinite groups. Now, the study of centralizers in locally finite groups is a well-established direction. There are a lot of results in this about centralizers in locally finite groups. And in particular, generalizing the Brouwer-Fowler theorem, Hartley showed that if a locally finite group has an element with finite centralizer, then the group also has a locally soluble subgroup of finite index. So this rules out any possibility for infinite simple groups and so on. Hucro shows that if that element X here has prime order, then the group even has a nilpotent subgroup of finite index. So we have very strong structural results about locally finite groups with finite centralizer of an element. Well, also locally finite CA groups have been described, and it's quite easy, and the description is more or less the same as for finite groups, in just the field F need not be finite, it can be just a locally finite group, a locally finite field of, again, of characteristic 2. So that was easy. On the other hand, until recently, there were almost no results on centralizers in profinite groups. At least no results that really have origin in the theory of finite groups. And this can be easily explained by the fact that just there is no natural connection between finite groups with certain restriction on centralizers and profinite groups. And in simple terms, if we have a centralizer in a subgroup, is always a subgroup of a centralizer. And so in locally finite groups with restriction on centralizers, it's easy to just deal with finite subgroups. On the other hand, a centralizer in a quotient, in general, is not quotient of a centralizer. And so when we have a profinite group with restriction on centralizer, we really can say nothing about finite quotients. And that's the basic difficulty. Well, we have this difficulty, but on the other hand, infinite CA group have important role in certain study, in particular in geometric group theory. And they had important role in the solution of so-called Tarski problems. It happens that limit groups, residually free groups, they all have that property. Centralizers are abelian. And in some works of Zalewski, Koshlyukova, Zapata, some important pro-P groups were shown to have this property. So Pavel Zalewski, who is my colleague in, of course, in Brasilia, was telling me that it would be nice to have some structural theorems on profinite CA groups. But for some time I was very skeptical about this project. First reason for my skepticism is precisely what I just told you. There is no direct way to connect finite CA groups with profinite CA groups. And another observation is that, well, if you look at finite CA group, first observation you see that seal of subgroups, since they are nilpotent, they must be abelian. And finite group with abelian seal of subgroups, you understand that this is a very strong, very restrictive property. Now in profinite groups, you just don't have it. A pro-P group can have trivial center. So without this basic property, I just could not imagine that one can do anything about this. And the third problem for me was that actually we didn't know what we want to prove. He said structural theory, but what it means, what is structural theory? So we didn't have means to prove things, and we didn't know what we want to prove, we didn't know how to start. I was very skeptical for some time, but after a period of conversations, actually some useful ideas were born, and Teo Zapata joined us in this project, and then we really proved some results. And first thing that we proved was the theorem that a profinite CA group is either is virtually abelian. Virtually means it has an open subgroup, that is a subgroup of finite index. Either is virtually abelian or virtually pro-P. So basically this reduces all problems about such groups to pro-P, to the pro-P case. And then we really obtained structural information about the group. So suppose our group is virtually abelian, that is, it has an abelian subgroup of finite index. Then it's easy to see that it has a unique maximal normal abelian subgroup of finite index. We denote it by n, And then we see that there is only few possibilities for the finite quotient G over n. This happened to be either a generalized quaternion group or the group S, or of course it can be a cyclic group, or the group SL23. And in particular, it happens that in this case, our group is necessarily prosoluble. So SL23 is a very small group. It's just a semi-direct product of a quaternion group of order 8 by an automorphism of order 3. By the way, quaternion group cannot be a subgroup of a CA group because it is nilpotent, it's part of a centralizer, but it's not abelian. But as the theorem shows, it really can be a quotient of a CA group. And we have examples for all these cases really occur. Such groups really can be CA groups. So this tells us about everything we want to know about the case when the group is virtually abelian. Now, if the group is virtually pro-P, then, well, if it is prosoluble, we can write it as a product of a normal, again, maximal normal pro-P group, which is open of finite index, and the finite subgroup K, where K is a very small group. It's either cyclic or metacyclic Frobenius group. Metacyclic means that it's an extension of a cyclic group by a cyclic group. So again, very small group. Or if it's not prosoluble, then the quotient over maximal normal 2 subgroup must be almost simple. Almost simple means that it's, well, more or less simple, but also can be extended by some automorphisms. Such groups also are well understood due to classification, of course. And so this gives us a pretty detailed information about profinite CA groups. But again, modulo pro-P groups. We really have very little to say about pro-P groups. Well, still there are some questions. In particular, of all those possibilities that I mentioned, we have all examples, except we don't have an example of a profinite CA group which wouldn't be prosoluble. Actually, all our examples are prosoluble, and it's an open question whether such group is always prosoluble. Okay, having proved those results about profinite CA groups, we moved on. It seems the techniques that was created, and I will talk about it later, can be also applied to other situations. In particular, I studied so-called CN groups. These are profinite groups in which all centralizers are pro-nilpotent. Finite groups with this property is a classical subject due to the role that they played in the proof of the Phi-Thompson theorem. So Phi-Thompson theorem was proved in 1963. In 1961, there was a paper by Veit, Hall, and Thompson that showed that finite group of odd order with this property are soluble. And also in 61, Suzuki studied such groups. And studying such groups, he discovered a new family of finite simple groups that now bears his name. So these groups are a really important subject. But now what happened is that profinite CN groups actually not much more complicated than finite ones. And so we proved that a profinite CN group is virtually pro-nilpotent. And moreover, if we have a profinite group with this property, of course it has a unique maximal normal pro-nilpotent subgroup denoted by F. And then we have only few possibilities for the finite quotient G over F. Such quotient can be either cyclic, or it can be a direct product of a cyclic group of odd order and a generalized quaternion group, or it can be a Frobenius group with certain restrictions. And in that case, actually, we can also say that F should be just a pro-P group for some prime P. Or it can be, the quotient can be also isomorphic to the familiar group SL23. And in that particular case, the pro-nilpotent radical must really be nilpotent, just pro-nilpotent. Not just pro-nilpotent, it must be nilpotent. Or the final case, G over F can be again almost simple, and in that case F must be a Pro2 group. And for this theorem we have really examples of we have examples of almost simple groups, say non-prosoluble groups that are Cn groups. And an immediate corollary of the theorem that I just cited is that prosoluble radical in such group is either the whole group, that is either the group is prosoluble or the prosoluble radical is a 2 group. And this was established by Suzuki in 1961, of course using absolutely different methods. Okay, it seems the techniques that we created can be applied to many, many situations. I just would like to mention just one. So in 1957, Graham-Higman studied finite groups in which all elements have prime power order. Prime is not fixed here, so for each element x, there exists a prime such that x has prime power order. But of course, it's not difficult to understand that such groups must be Cn groups. That is, here all centralizers are actually P groups, so centralizers are nilpotent and okay, Higman described in great details finite soluble groups with this property. Nowadays also non-soluble groups are well understood. In particular, there are just 8 finite simple groups with this property. I gave the list here, but we will not use it. Now, studying profinite groups with this property, that is, profinite groups in which all centralizers are pro-P groups. Maybe not so interesting because, first of all, we have already detailed description of profinite groups with pronilpotent centralizer. And another observation is that in this case, really, profinite group with this property is the inverse limit of finite groups with that property. So this really wouldn't be such an interesting problem. So instead, we considered groups in which all centralizers are virtually pro-P. And P is not fixed here. For every element x, there exists prime P such that the centralizer of x is virtually pro-P. Okay, the result is that this happens if and only if there exists a unique prime P such that all centralizers are virtually pro-P. And that's a rather surprising fact. A priori, it was absolutely unclear why such a prime P should be unique. But yes, we got it. Okay, and I could go on and mention other results in the same spirit, but I think maybe it's better if I also describe some points in the proof of the theorem that if G is a profinite CA group, then it must be either virtually abelian or virtually pro-P. First, we observe that if G is pronilpotent, then it's a direct product of its seal of subgroups. And so if it's not pro-P, it has at least 2 different seal of subgroups, they commute, and so since centralizers are abelian, the whole group must be abelian. So pronilpotent groups with this property are either abelian or pro-P. And so what we really want to prove is that our group G is virtually pronilpotent. Now, how we do it? A useful technical tool is provided by the following lemma. Suppose G is a profinite CA group having a non-trivial normal subgroup N, such that G over N is infinite, and N has order coprime with the quotient G over N. Then the whole group G is abelian. So coprimeness of order in infinite group here in this sense should be understood in the profinite context. The most simple way to explain it is just in every finite continuous image of the group G, the image of N has order coprime with the image of the quotient G over N. Okay, so hypothesis in this lemma is very simple. It's just like in the classical Schurz-Eschenhaus theorem. But the conclusion is surprisingly strong. And this rules out a lot of possible configurations in our group. And really, it shows a very restrictive property of in our groups. Anyway, so I will not talk about the proof of this lemma, rather I will explain how it was used. But just I recall some basics about profinite groups. Seal of theory for profinite groups is as good as it is for finite groups. A profinite group has a seal of subgroup for each prime p that dividing its order, and seal of subgroups are conjugate. Moreover, if G is a prosoluble group, then it has a seal of system. By seal of system, we mean a system of seal of subgroups, seal of p subgroups, one for each prime p dividing the order, such that the product of any two of them is again a subgroup. So it's well known from finite group theory. A finite group is soluble if and only if it has a seal of system. And the same holds for profinite groups. A profinite group is prosoluble if and only if it has seal of system. Now, given a seal of system, by the way, seal of systems also are conjugate. So we have it as, it's a nice property that holds in profinite groups as it holds in finite groups, of course. So, given a seal of system, we denote by T the centralizer of the intersection of all normalizers of seal of subgroups in that system. And this intersection is called system normalizer. From finite group theory, it's known that system normalizer are always pro-nilpotent. In the finite case, nilpotent, of course. Any two of them are conjugate. And we also have that G can always be written as a so-called pro-nilpotent residual K and the system normalizer. So pro-nilpotent residual is just the intersection of all terms of the lower central series of the group, and also it can be defined as the unique smallest normal subgroup, such that the quotient over that subgroup is pro-nilpotent. So if G is a prosoluble group, we can always write G as a product of this residual with system normalizer. Okay. Now, we also need a concept of fitting height of G. It's clear that every finite soluble group can be written as an extension of several finite nilpotent subgroups. So that minimal number of finite nilpotent quotients in such extension is called fitting height of G, and it's denoted usually by H of G. In the prosoluble context, this parameter usually is not often used. We will understand it in the sense that G has a normal series of lengths at most H, with all of whose quotients are pro-nilpotent. In general, even a prosoluble group doesn't have to have a series of such kind with finite lengths. But just we will see in a few minutes that in our case, really all groups that emerge have finite fitting height. Okay, now suppose G is a prosoluble CA group, and suppose it has an infinite system normalizer T. Using certain stuff, okay, we can choose an infinite. I'm now talking about one particular case of the proof because it's just an illustrative case. It could be that infinite P subgroup doesn't exist, but that case can be treated in a similar manner. So we just consider the case when T contains an infinite P subgroup A. And since T is a system normalizer, A normalizes some whole P dash subgroup H of G. And now, because of that technical lemma, we have a precisely situation where we can use it, and it follows that H is abelian. So G is now a prosoluble group with an abelian whole P dash subgroup. And now, it's the very beginning of what is now called Hall-Higman theory. With such conditions, any finite group has fitting height at most 3. And we just extend this result from finite group. to a profinite case and just conclude that in this case our group G has fitting height at most 3. So this is one particular case, but it really covers a lot of possibilities. And in general, of course, could happen that we have a prosoluble CA group with finite system normalizer. But fact is that also in this case we can bound the fitting height of the group. How we do it? Okay, right, K1 is just group G, K2 is a residual of K1, and K3 the residual of K2. Okay, we can choose a seal of system in the group G, and this gives rise to seal of systems also in K2 and K3. And now we also can, we choose a system normalizer for corresponding seal of systems. And we see that, say, T1 normalizes T2, T2 normalizes T3, they normalize, so we will use this fact. If at least one of these system normalizers is infinite, then because of the previous argument, it follows that fitting height of K3 is at most 3, and then fitting height of the whole group is at most 5. And if all of them are finite, then we just consider the subgroups that they generate. And analysis shows that this is a finite CA group of fitting height 3. Now, I was complaining in the beginning that we cannot use results on finite CA groups. But actually now we can do precisely this. This product T1, T2, T3 would be a finite CA group of fitting height 3 according to classifications that I gave in the very beginning. That's just impossible. All finite soluble CA groups have fitting height at most 2. So that's a contradiction. And this shows that at least one of these system normalizers must be really infinite, and therefore our group has fitting height at most 5. So what we proved so far is that if our CA group is prosoluble, then it has fitting height 5. So far this doesn't tell us much about general case when the group is not prosoluble. Okay, now we'll look closely at the class of all finite groups in which soluble subgroups have fitting height at most 5. This class is not doesn't necessarily contain only soluble groups. It's already a general class of groups. Can be also, actually a lot of simple groups have this property. Well, first observation is quite obvious that subgroups of groups in this class again belong to that class. And what is less obvious is that this class actually is closed with respect to taken quotients. And, okay, this is less obvious, but this can be proved. And therefore, any profinite CA group is pro-X. And that's an important moment, since we now know that any not necessarily prosoluble groups, just any profinite CA group is pro-X. And again, in the beginning, I was complaining that we have no information about finite quotients of our group. But now, actually, we know quite a lot. This is a well-behaved class, and we just need to understand the structure of groups in this class and see if we can use it to analyze our profinite groups. Okay. We now need a concept of non-soluble lengths of a finite group. This concept implicitly was used already in the famous paper by Hall and Higman of 1956. That paper where they reduced the restricted Birdside problem to the case of nilpotent groups. Explicitly, this concept was introduced in one of my recent papers with Evgeny Khukhro. So every finite group has a normal series whose factors are either soluble or direct product of non-abelian simple groups. And so the minimal number of such non-soluble factors in such a series will be called non-soluble lengths and denoted by lambda of G. Okay. So we proved several results about this parameter, one of which is that the non-soluble length of a finite group G does not exceed the maximum fitting height of soluble subgroups of G. Whenever you have a finite group, you just consider soluble subgroups, and they control also the non-soluble length. That's just a fact. And this fact can be used to show that in our profinite case, our group has a finite series, it has a normal series of finite lengths, all of whose quotients are either pronilpotent or Cartesian products of finite simple groups. This moment is similar to what John Wilson did in his analysis of compact torsion groups. And so our theorem now can be proved by induction on the length of this series. The final results. Okay, at this point we could just make the conclusion that our group has such series of lengths at most 35. But then the final results, also using classification of finite simple groups, shows that this length has actually this series has lengths at most 3. So now I would like to say a few more words about similarity between the ideas used in our proof and how the restricted Burnside problem was solved. So the restricted Burnside problem is, suppose G is a finite M generated group such that x to the n is 1 for all x in G. So this, in other terms, G is a finite M generated group of exponent n. The question is the order of G bounded in terms of M and N only. This is called the restricted Burnside problem, but actually it wasn't Burnside who suggested this. Burnside suggested a different kind of problem. It was in 1902, but then by the end of 1920s, in Germany, this problem served as an attempt to solve the general Burnside problem. And it was formulated, I think the first publication was in a work by Grün in 1939. And it was long after Burnside died. Anyway, so the problem was open for many years. And then Hall and Higman came up with an excellent idea. And they reduced the problem to the case when the group G is a nilpotent group. So what exactly they did? I mentioned their name several times during the talk, so maybe I need to really pay some tribute. Hall Higman, 1956. So they proved the following theorem. Let G be finite of exponent n. So exponent n means precisely this property. Okay, then G has normal series of n-bounded. N-bounded means that it's bounded by certain function depending only on n of n-bounded length, such that all quotients are either nilpotent or direct product of simple groups. Either nilpotent or direct product of simple groups. And what this does, the group G in general can be very big, but Hall-Higman theory breaks the group into smaller pieces, and it shows that we have only finitely many, and actually boundedly many such pieces. Then later, the quotients. And basically, this reduces the question to the groups in which this series has length 1. That is, the group is either direct product of simple groups or nilpotent. Simple groups were handled using classification of finite simple groups. Nilpotent groups were solved. The case of nilpotent groups was solved by Zermanov in 1989 using Lie algebras, and eventually the whole problem was solved. But of course, the basic, most important step was done. Well, most important at the time step was done in this very seminal, important paper by Hall and Higman. Then there was another similar development about the problem if every torsion compact group would be locally finite. Well, that was a famous problem. Is every every compact torsion group locally finite. Again, this problem was solved again by Zermanov following his solution of the restricted Berzai problem. But before, there was an important paper by John Wilson, also paper that I mentioned here. Wilson shows that if the group G is compact torsion, then G has a finite series again, like here. All of whose quotients are either Cartesian products of simples or pro-P. This Wilson's theorem is very similar to what Hall-Higman did. And again, here the quotients that were that are Cartesian product of simple groups were handled using classification of finite simple groups. In the case when G is a pro-P group, was handled using Zermanov's techniques from the solution of the restricted Berzeit problem. So eventually what we did was similar. We broke our group in such smaller pieces which are either pro-nilpotent or Cartesian product of simple groups. The simple groups were handled using classification of finite groups. Pro-nilpotent case, in a sense, still open and probably will be open for a long time. And it means that we just don't have much information about pro-P groups, which are CA groups. So, but that's maybe would be an open problem, perhaps for a long time. But now I would like to finish, and so thank you so much.
Questions? Comments?
Well, actually, I have two comments. First comment is that when speaker was talking about nilpotent centralizers, he was continuing to say we, but actually it was his only result. We are not me, neither me nor Zapata was not involved in this. And second comment, it is connected to his last comment that actually we have very little about about pro-P groups having this CR property. But there is another problem which is still left. When he says about virtually free pro-P groups, we have actually the problem of it is reduced actually to the open and also very important problem of pro-P group have, if we have a pro-P group and have a co-prime automorphism group, what is the fixed point of pro-P group, right? If we restrict fixed points of pro-P group, right, how do we restrict actually the pro-P group itself? And what we know only if this fixed points is trivial, then the group is actually nilpotent. But any other restriction, right? We don't know anything, and it is basically clear that any restriction, like abelian centralizer of even finitely generated fixed point groups, right, should give more restriction to the pro-P group, because for free pro-P group, right, the subgroup of fixed points is always infinitely generated.
So, any more questions? I would say, if not, let's send the speakers.
Okay, at this time is going to the down.